The greatest discoveries in space were not the result of careful planning. They were happy accidents. Astronomers aiming their telescopes at one thing stumbled upon something entirely different, something bizarre that rewrote the rules of reality. We are about to journey through 25 of the most mind-bending space anomalies ever found by chance. By the end, you will understand just how strange and unpredictable our universe truly is. What is the mysterious signal so powerful an astronomer scrawled "wow" next to the data, and why has it never been heard again? And what is the true nature of the strange, tumbling object that entered our solar system and defied all explanation? What do you believe is the most profound secret the cosmos is still keeping from us? It was a quiet night in August 1977. A routine survey of the sky by the Big Ear radio telescope at Ohio State University. The massive instrument was methodically listening to the cosmos, collecting streams of data that usually amounted to nothing more than cosmic static. But on this particular night, the silence was broken. For 72 seconds, a signal blasted through the void, so powerful and so strange that it defied all natural explanation. It was a narrowband radio signal, precisely at the frequency hydrogen atoms emit, a frequency many scientists considered a logical channel for interstellar communication. Volunteer astronomer Jerry Amon was reviewing the computer printout days later, his eyes scanning the columns of letters and numbers when he saw it. A sequence so intense he circled it in red pen and in the margin wrote a single powerful word: "Wow." The wow signal was everything astronomers would expect from a deliberate transmission and nothing like any known natural phenomenon. It was incredibly strong, then it vanished completely, never to be heard again. For decades, that 72-second burst has taunted science. Was it a message? The most tantalizing theory points to an intelligent origin, a beacon from a civilization far away, flickering on and off in a moment of cosmic coincidence. Yet skeptics search for other answers. Some proposed it was a signal reflected off a piece of space debris, or a previously unknown cometary emission, though later investigations found no comets in the right part of the sky. The very nature of the signal, its brevity and uniqueness, is what guards its secret. It remains a solitary shout in the dark, a question mark etched in red ink that continues to challenge our place in the universe. If it was a hello, why was there never a goodbye? That solitary, unanswered signal was a whisper compared to the physical object that raced into our view decades later. In October 2017, a telescope in Hawaii spotted something moving too fast to be from our own solar system. It was the first visitor ever detected from interstellar space, and astronomers named it Oumuamua, a Hawaiian word for scout. This was not a typical comet or asteroid. As telescopes around the world swiveled to track its hasty departure, it revealed a series of puzzles that shook the foundations of planetary science. Its path was the first clue. Oumuamua was not orbiting our sun. It was merely passing through, a cosmic tourist on a one-way trip from an unknown star system. But its trajectory held a mystery. As it sped away, it exhibited a slight but undeniable acceleration, a push that could not be explained by the sun's gravity alone. Comets often get a similar push from outgassing when sunlight vaporizes their ice, creating a jet of material that acts like a tiny engine. Yet Oumuamua showed no visible coma, the classic cloud of gas and dust that surrounds a comet. There was no detectable outgassing, no tail. So what was pushing it? The strangeness deepened with its shape. By measuring how its brightness changed dramatically over hours, astronomers deduced it was tumbling end over end. The best explanation was an extremely elongated form, a shape unlike any asteroid we have ever seen in our own solar system. It was perhaps 10 times longer than it was wide, a dark red, cigar-shaped object tumbling through the void. How does a natural object form with such a bizarre geometry? The scientific community scrambled for natural explanations. Perhaps it was a shard from a planet shattered by a cosmic collision, or a rare fractal-like dust aggregate. But the unexplained acceleration remained the central, nagging problem. This is where the debate turned controversial. Harvard astrophysicist Avi Loeb proposed a startling hypothesis. What if Oumuamua's acceleration was not from invisible gas, but from sunlight itself? He suggested it could be a light sail, a vast, thin sheet designed to catch the radiation pressure from stars for propulsion. In this theory, its unusual shape and motion were not quirks of nature, but signs of technology. It could be a derelict probe, a piece of advanced alien machinery drifting silently between the stars. The mainstream astronomy community largely rejected this idea, favoring the search for a natural, if exotic, cause. Yet Loeb's argument highlighted a profound point. When we encounter something truly unprecedented, how do we know when we are looking at a natural oddity or something else entirely? Oumuamua is now long gone, a faint speck vanishing into the black, leaving behind only a trail of data and a universe of questions. Was it a cosmic iceberg, a strange new type of asteroid, or was it, as some still wonder, our first brush with an artifact from another world? While Oumuamua presented a mystery of motion, other anomalies captivate us with their bizarre and unpredictable light. Far from our solar system, a star named KIC 8462852, better known as Tabby's star, began behaving in a way no one had ever seen. It was not professional astronomers who first noticed its oddities, but volunteers, everyday people sifting through public data from NASA's Kepler telescope on the Planet Hunters website. They were looking for the telltale, regular dips in starlight that occur when a planet passes in front of its sun. What they found was something entirely different. Tabby's star dimmed erratically, sometimes by just a tiny fraction, other times by a staggering 22%. This was not the clean, repeating signal of an orbiting planet. It was a chaotic, unpredictable flickering, as if massive, irregular shapes were drifting in front of the star. The scientific community was stunned. What could possibly block that much light? The most exciting and controversial theory pointed to alien technology. Astronomer Jason Wright suggested we might be witnessing a Dyson swarm, a vast collection of energy-collecting structures built by an advanced civilization. The idea captured the public's imagination, a cosmic engineering project on an unimaginable scale. Yet science sought more natural answers. Could it be a colossal cloud of dust from a shattered planet, or a family of millions of comets passing in a tight, chaotic formation? Further observations revealed the star also dims gradually over long periods, a sign that fine dust is likely the main culprit. While the alien megastructure hypothesis has faded, the true nature of the dust cloud remains unknown. What process creates such an immense, clumpy, and dynamic shroud around a star? Tabby's star reminds us that citizen scientists can still make profound discoveries, and that the universe is capable of constructing things we do not yet understand. From a star shrouded in mystery, we turn to a nebula with an impossibly perfect shape. In the constellation Monoceros, a dying star is expelling its outer layers, creating what astronomers expected to be a beautiful, chaotic cloud. When they first saw it in visible light, they named it the red rectangle for its striking color and form. But it was an accidental discovery in infrared light that revealed its true, shocking geometry. This was not a messy sphere or a simple bubble. The red rectangle nebula displayed a near-perfect, symmetrical structure of concentric rectangles, like a cosmic ladder or a set of glowing, X-shaped rungs extending into space. How does a star, in its final death throes, create such precise, angular shapes? The answer lies in a hidden dance. At the heart of the nebula are two stars, not one, locked in a tight orbit. As the primary star dies, it expels gas and dust, but the gravitational tug of its companion star funnels this material into two opposing cones. From our vantage point on Earth, we are looking directly down the barrel of these cones, and the edges of the overlapping cones create the illusion of a rectangle. The precise alignment and the density of dust particles create the ladder like rungs through a complex process of light scattering. This celestial accident of perspective shows us that what appears to be an impossible, artificial structure is actually the signature of a hidden binary system. The red rectangle challenges our artistic vision of a dying star, proving that the cosmos can craft geometry as perfect as any draftsman's tool, all through the simple, relentless application of physical laws. Our own galaxy is racing through the void at over 1 million miles per hour, pulled by a force we cannot see. This is the Great Attractor, a colossal gravitational anomaly located in the depths of intergalactic space. Astronomers did not find it by looking directly at it. They discovered it by accident, by meticulously mapping the motions of thousands of galaxies and realizing they were all flowing like rivers to the sea toward a single, invisible point. Our entire Milky Way, along with our local group of galaxies, is caught in this cosmic current. The great mystery is what exactly is pulling us. The region lies in a direction of the sky obscured by the dust and stars of our own galaxy's central bulge, a zone of avoidance that makes observations incredibly difficult. Peering through this cosmic veil, astronomers have since found that the Great Attractor is not the final destination. It is merely a waypoint on a much larger journey, a smaller pull within an immense structure known as the Laniakea supercluster, which is itself being drawn toward an even more massive concentration of mass called the Shapley Attractor. The Great Attractor taught us a profound lesson about the cosmos, that the most powerful forces can remain hidden in plain sight, their presence revealed only by the silent, relentless motion of everything around them. From an invisible force that tugs at galaxies, we turn to a galaxy that is a vision of impossible perfection. In 1950, astronomer Art Hogue discovered a celestial oddity, a galaxy now known as Hogue's object. Through the telescope, it appeared as a nearly perfect ring of brilliant blue stars, encircling a golden, spherical core with a seemingly empty, dark gap between them. It looked less like a natural formation and more like a cosmic donut or a giant's thrown smoke ring. This was not a spiral galaxy like our Milky Way, nor a common elliptical galaxy. It was a ring galaxy, an exceptionally rare type whose formation remains a topic of debate. The leading theory suggests a galactic collision, a bullseye impact where a smaller galaxy pierced the heart of a larger disk galaxy billions of years ago. The gravitational shockwave would have sent stars rippling outward, much like a drop of water falling into a still pond, creating that expanding ring of star formation. The central core remained relatively undisturbed, leaving the two distinct parts we see today. Hogue's object is a frozen moment of cosmic violence, a testament to the chaotic origins of breathtaking beauty. While Hogue's object is a confirmed and beautiful mystery, another orbiting object is shrouded in myth and misinformation. For decades, stories have circulated about the Black Knight satellite, an alleged alien artifact in a near-polar orbit around Earth. Tales describe it as an ancient, intelligent probe watching us for thousands of years. The legend grew from a combination of misidentified objects and creative interpretation. In 1960, a newspaper reported that the US Navy had detected a dark object in orbit, which turned out to be a piece of orbital debris, likely a discarded casing from a Corona spy satellite mission. The most famous image associated with the Black Knight is actually a thermal blanket lost during a space shuttle Endeavour spacewalk in 1998. Astronauts accidentally let it go, and it slowly tumbled away, a mundane piece of insulation mistaken for a mysterious craft. Even earlier, unusual radio signals reported by Nikola Tesla in the 1890s were later attributed to natural celestial sources like Jupiter. The Black Knight is a fascinating cultural anomaly, a patchwork of Cold War anxiety, genuine space debris, and our deep-seated desire to find evidence that we are not alone. It shows how easily the unknown can be woven into a compelling, though ultimately unsubstantiated, story. The real mystery is not in the sky, but in our own minds and our endless capacity to see patterns and purpose in the random noise of the cosmos. The scale of cosmic emptiness can be just as staggering as its structures. While mapping the large-scale distribution of galaxies in the 1980s, astronomers stumbled upon a region of nothingness so vast it defied belief. This is the Boötes Void, a spherical region of space roughly 330 million light-years across. To grasp that scale, if you placed our Milky Way at its center, the nearest edge of this void would be over 160 million light-years away in every direction. In a universe where galaxies cluster like cities, the Boötes Void is a continent-sized desert of near-total emptiness. Where a typical region of space that size should contain at least 10,000 galaxies, the Boötes Void holds only a few dozen. Its discovery was a profound shock, challenging our fundamental models of how the universe organized itself after the Big Bang. The prevailing theory suggests the cosmos has a bubbly, frothy structure, with vast cosmic voids surrounded by filaments and walls of galaxies like a cosmic sponge. But the Boötes Void is so immense it pushes this idea to its breaking point. How could a void this large form so early in the universe's history? Some theorists have proposed even more exotic ideas, suggesting it could be the imprint of a collision with a parallel universe in the multiverse, a scar left on the fabric of our own reality. While that remains highly speculative, the sheer existence of the Boötes Void forces us to question if we truly understand the rules of cosmic construction. It is a chilling reminder that the universe is not just full of wonders, but also of immense, inexplicable absences. Even as we map the great voids between galaxies, a tiny, persistent mystery was unfolding much closer to home, right in our own cosmic backyard. The Pioneer 10 and 11 spacecraft, having completed their missions to Jupiter and Saturn, were on their way out of the solar system, becoming humanity's first emissaries to the stars. But as scientists tracked their faint radio signals across billions of miles, they noticed something deeply wrong. Both spacecraft were slowing down. They were experiencing a tiny, constant, and completely unexplained deceleration back toward the Sun. This was the Pioneer anomaly, a deviation so small it was barely measurable, yet it defied the known laws of gravity for over 2 decades. It was a minuscule tug, a force 10 billion times weaker than Earth's gravity, but it was there and it was real. For years, this tiny glitch in the data haunted physicists. Was it evidence of a flaw in Einstein's theory of general relativity? Could it be the fingerprint of dark matter exerting a subtle drag, or perhaps a sign of entirely new physics operating at the scale of the solar system? Some proposed more mundane causes, like a slow, undetected leak of propellant from the spacecraft's thrusters, acting like a tiny, continuous brake. The mystery persisted because the signal was so faint and the potential explanation so profound. Solving it required a monumental effort in scientific archaeology. A dedicated team spent years recovering old data tapes and telemetry records, even tracking down the original engineers who had built the probes in the 1970s. They painstakingly built a computer model of the spacecraft, accounting for every possible source of force, from the faint pressure of sunlight to the heat emitted by their radioactive power sources. And then they found the culprit. It was not new physics, it was heat. The Pioneer spacecraft were powered by plutonium, and that plutonium generated heat which the spacecraft radiated away into space. The team realized that this thermal radiation was not perfectly symmetrical. A little more heat was being emitted from the back of the spacecraft's main antenna dish than from the front. This imbalance created a tiny recoil force, a gentle but constant push, not unlike the push you feel when you shine a bright flashlight. This thermal recoil force was exactly the right magnitude to account for the mysterious deceleration. The Pioneer anomaly was solved. It was a lesson in humility and meticulousness, a reminder that the universe often hides its secrets not in grand gestures, but in the whisper-quiet details that only reveal themselves to those with the patience to listen. Sometimes the most profound truths are hidden in a persistent, low hum. While the pioneer anomaly was a whisper in the data, another team of scientists in the 1960s was plagued by a literal physical noise. At Bell Labs in New Jersey, radio astronomers Arno Penzias and Robert Wilson were testing a massive, ultra-sensitive horn antenna, originally built for satellite communication. Their goal was straightforward: to measure radio waves from our own galaxy. But their work was constantly hampered by an annoying, persistent hiss, a uniform static that seemed to come from every direction in the sky. This noise was relentless, and it made their precise astronomical work nearly impossible. They assumed it was simple interference. Perhaps it was radio chatter from nearby New York City, or maybe it was a flaw in their equipment. They meticulously checked every component. They even famously evicted a pair of pigeons that had nested in the giant horn, cleaning out what they described as a white dielectric material, a polite term for bird droppings which they suspected could be causing the signal. But even after scrubbing the antenna clean and shooing the pigeons away, the hiss remained. It was an inescapable, omnipresent background noise that defied all their efforts at elimination. This annoying anomaly was, in fact, the echo of creation itself. Unbeknownst to Penzias and Wilson, a team of physicists at Princeton University, led by Robert Dick, was actively searching for this very signal. They were pursuing a prediction of the Big Bang theory, that if the universe began in a hot, dense state, it should have left behind a faint, cool afterglow, a remnant radiation bath that would now permeate all of space. When Penzias and Wilson, frustrated, heard about this theoretical work, a stunning realization dawned. The irritating noise plaguing their antenna was not a technical fault. It was the cosmic microwave background radiation. They had accidentally stumbled upon the oldest light in the universe, cooled and stretched by billions of years of cosmic expansion into the microwave part of the spectrum. This discovery was monumental. It was the final, crucial piece of evidence that cemented the Big Bang theory as the dominant model of the universe's origin, decisively beating out the rival steady-state theory. That faint hiss was the cooled remnant of the universe's fiery birth, a snapshot of the cosmos when it was just 380,000 years old. For their accidental discovery, a finding born from trying to clear pigeon waste from a giant antenna, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics in 1978. It stands as one of the greatest examples of a scientific break, through emerging not from a direct quest, but from the careful and persistent investigation of an unexplained anomaly. The entire universe, it turns out, is ringing with the faint whisper of its own beginning. That faint cosmic whisper was the echo of the universe's birth, but some signals are born in a violent, screaming instant. In April 2020, a sudden and colossal blast of radio waves erupted from deep within our own Milky Way galaxy. This was no gentle hiss, it was a fast radio burst, one of the most energetic and mysterious phenomena in the cosmos. For over a decade, these bursts had baffled astronomers, appearing as brilliant millisecond flashes from galaxies billions of light-years away. Their immense power defied explanation, with a single burst releasing more energy than our Sun emits in 80 years, all in the blink of an eye. Theories for their origin ranged from the cataclysmic, like colliding neutron stars, to the purely speculative, including advanced alien propulsion systems. The mystery deepened because they came from so far away, their signals scrambled by their long journey through intergalactic space, but this time was different. The source was right next door, cosmically speaking, and it was caught in the act. The discovery was a happy accident. The burst was detected not by a single instrument, but by a suite of telescopes across the globe, some of which were not even pointed at the right part of the sky for a targeted search. They were simply monitoring the cosmos, and this explosive event was so bright it was impossible to miss. The data immediately pinpointed the culprit, a known object within our own galaxy called SGR 1935 plus 215. It was a magnetar. A magnetar is a type of neutron star, the collapsed, ultra-dense core of a giant star that went supernova. But a magnetar is a neutron star turned up to 11. It possesses a magnetic field so unimaginably powerful it would erase the data from every credit card on Earth from halfway across the solar system. The physics around such an object are extreme beyond comprehension. The leading theory suggests that these intense bursts are starquakes. The magnetar's crust, a rigid lattice of iron nuclei, is under immense strain from the twisting magnetic fields. Occasionally, this crust cracks, releasing a cataclysmic shockwave of energy. Think of it like snapping a giant cosmic rubber band. In that instant, a massive wave of particles and radiation is launched into space, and when this wave interacts with the magnetar's own intense magnetic field, it gets converted into a brilliant, coherent pulse of radio waves that we detect as a fast radio burst. This single, local detection did not solve every mystery surrounding these bursts, as some from deeper space may still have other origins, but it provided the first undeniable proof that magnetars are at least one source of these cosmic fireworks. It was a monumental breakthrough, connecting a long-standing enigma to a known, if utterly bizarre, celestial object. The universe, it seems, can create its most powerful flashes not in the vast emptiness between galaxies, but in the tortured, magnetic death throes of a city-sized star right in our own cosmic neighborhood. While magnetars create brilliant, momentary flashes, other stellar mysteries unfold in a slow, creeping dimness that lasts for years. Far beyond Tabby's star lies an even more extreme enigma, a star whose light has faded in a way that seems almost deliberate. This star, located over 1,300 light-years away, was observed by the Kepler telescope dimming by an astonishing 80%. Unlike the erratic dips of Tabby's star, this dimming was slow, steady, and monstrously large. Imagine a light in your house gradually fading over several years until it is barely a glimmer. For a star to behave this way, something truly colossal must be blocking its light. The sheer scale of the dimming makes the alien megastructure hypothesis seem almost reasonable, as if a Dyson sphere under construction was slowly eclipsing its sun. Yet, just as with its more famous cousin, the most plausible explanation points to a titanic cloud of dust. The dust particles required to cause such a profound and gradual dimming would have to be incredibly fine, almost like cosmic soot, and exist in a complex, clumpy orbit around the star. The very existence of these dust-shrouded stars tells us that planetary systems can go through chaotic, violent phases, where perhaps entire worlds are pulverized into vast rings of obscuring debris. These are not just stars, they are crime scenes on a cosmic scale, and we are left to piece together what catastrophic event could create such an immense and long-lasting veil. From stars being hidden, we turn to galaxies that are actively consuming. Our own Milky Way is a cosmic cannibal, a fact accidentally revealed not by looking at its bright center, but at the faint wisps of light surrounding it. In the early 2000s, astronomers mapping the outer halo of our galaxy stumbled upon a vast stream of stars arcing across the sky. This was no orderly spiral arm, it was a stellar river, a ghostly remnant of a smaller dwarf galaxy that had been torn apart and swallowed by the Milky Way's immense gravity. This structure, named the Sagittarius Dwarf Stream, is the evidence of a meal still in progress, a galaxy being stretched into a long filament of stars that will eventually be fully absorbed into our own. The discovery was a shock, revealing that galaxy growth is a violent, ongoing process of accretion. This cannibalism is not unique to us. When the Hubble Space Telescope peered into the deep field, capturing images of countless distant galaxies, it found even more dramatic evidence. Some galaxies showed long, faint tidal tails, plumes of stars being ripped away during close encounters. Others had bizarre, distorted shapes and multiple nuclei at their centers, the unmistakable signature of a recent merger where one galaxy is consuming another. These are not quick events, but slow, gravitational feasts that take hundreds of millions of years. Every massive galaxy we see today, including our own, likely built its bulk through a long history of such cosmic consumption. The serene beauty of a spiral galaxy in a photograph belies a violent past, a history of collisions and mergers that shaped the universe we inhabit. What appears as a peaceful island of stars is often a predator, its growth written in the faint, ghostly streams of its digested prey. Even our own moon can hide things in plain sight. The Soviet Lunokhod 1 rover, a robotic vehicle that trundled across the lunar surface in the 1970s, carried a sophisticated French-built retroreflector, a panel of prisms designed to bounce laser beams from Earth directly back to their source. These devices are priceless for science, allowing us to measure the Earth-Moon distance with millimeter precision, testing gravity and tracking the moon's slow drift away from our planet. But after the mission ended, Lunokhod 1 fell silent and its exact location was lost. For nearly 4 decades, this valuable scientific instrument was just a forgotten piece of lunar junk, its precise coordinates unknown. Then, in 2010, a team analyzing old orbital images from NASA, a lunar reconnaissance orbiter, made a lucky guess. They spotted what they thought was the rover and, on a whim, fired a laser pulse from an observatory in New Mexico toward that patch of the moon. To their astonishment, a clear, strong signal bounced back. They had found the lost reflector. It was not just a recovery, it was a revelation. Lunokhod 1's retroreflector turned out to be one of the most efficient on the moon, providing brighter and more reliable returns than any other. Its accidental rediscovery revitalized lunar laser ranging, giving us a powerful new tool to probe the fundamental laws of physics from our own cosmic doorstep. From a lost device on the moon, we leap to a ghostly messenger from the depths of space. On September 22, 2017, a single, nearly massless particle called a neutrino struck a sensor deep in the ice of the South Pole. Neutrinos are cosmic ghosts capable of passing through entire planets without interacting with anything. Catching one is a monumental feat, but tracing its origin back across the cosmos seemed impossible. Yet this one was different. It carried an immense amount of energy, and its detection triggered an automated alert to telescopes around the world and in orbit. Within moments, the Fermi Gamma Ray Space Telescope swiveled to the direction the neutrino came from and spotted a brilliant flare of gamma rays from a blazar, a supermassive black hole at the heart of a distant galaxy, devouring matter and firing a jet of radiation directly at Earth. This was the birth of true multi-messenger astronomy. For the first time, we had used a neutrino, a particle of pure information, to pinpoint a cataclysmic event in the distant universe, then confirmed it with traditional light. It was like being handed a single, silent bullet from a gunfight happening in another city, and using it to find not just the shooter, but the exact room he was standing in. This accidental partnership between a ghost particle and a space telescope opened an entirely new window on the universe, allowing us to see the most violent cosmic engines not just with light, but with the very building blocks of matter itself. While that single neutrino pointed to a specific source, an even larger motion haunts the edges of our understanding. When scientists mapped the cosmic microwave background, the leftover heat from the Big Bang, they expected to see a perfectly uniform expansion in all directions. Instead, they found a subtle but shocking deviation, a mysterious drift they called the dark flow. It appears that entire clusters of galaxies, thousands of them, are moving in a coherent stream at incredible speeds toward a single point on the edge of the observable universe. This is not the local pull of the Great Attractor. This is a motion on the grandest possible scale, a current that seems to flow beyond the horizon of our visible cosmos. The most controversial explanation is that the gravity of something immense, something entirely outside our universe, is tugging on this vast sea of matter. It could be the gravitational pull from another universe in a vast multiverse, a cosmic structure so large it lies beyond the realm we can ever directly observe. The dark flow remains hotly debated, a statistical anomaly that some dismiss as a measurement error while others see as the first tantalizing clue of a reality far grander than we ever imagined. It hints that our universe may not be a solitary island, but one of many in an infinite ocean, and that the tides from those other shores can still be felt in the silent drift of the galaxies. The frenzy around Tabby's star began not in an ivory tower, but in the living rooms of everyday people. Volunteers on the Planet Hunter's website, sifting through the endless data from the Kepler telescope, were the first to flag this bizarre flickering. It was a triumph of citizen science, a collective effort that spotted what automated algorithms had missed. When the professional astronomers took a closer look, their initial reaction was sheer disbelief. This was not the clean, predictable dip of a planet. It was a chaotic, monstrous dimming, as if something vast and irregular was drifting in front of the star. The media, of course, seized on the most sensational possibility. The phrase alien megastructure exploded into headlines, capturing the world's imagination with the idea of a Dyson swarm, a colossal energy-harvesting array built by an advanced civilization. For a moment, it felt like we might be witnessing the ultimate discovery. But science, unlike speculation, demands evidence. A frantic global observing campaign was launched. Telescopes from the ground and in space, including the Hubble, turned their gaze toward this one enigmatic point of light. They monitored the star across different wavelengths of light, from infrared to ultraviolet, searching for a chemical fingerprint that would reveal the true nature of the obscuring material. The data began to tell a different story. When the star dimmed, it dimmed less in infrared light than in blue light. This was a crucial clue. Fine dust particles scatter blue light more effectively than red, much like our own atmosphere makes the sky appear blue. This fingerprint pointed decisively away from solid, opaque megastructures and toward a colossal, swirling cloud of dust. The material blocking the light was not a sleek, technological surface, but a mist of cosmic grime. The question then became, where could so much dust possibly come from? The explanations remain as strange as the original signal. Perhaps a family of exocomets, millions of them, are breaking up in a tight orbit around the star, creating a vast, clumpy shroud. Or maybe we are witnessing the aftermath of a planetary collision, a catastrophic event that pulverized entire worlds into a fine, opaque haze that now slowly drifts across the face of its sun. The alien megastructure theory faded, but it left behind a profound legacy. It reminded us that the most exciting discoveries often come from unexpected places, and that the universe is perfectly capable of constructing its own wonders, ones that are bizarre enough to challenge our imagination without requiring a single engineer. A planet has been found in a place where no planet should exist, orbiting the faint, dense corpse of a sun-like star known as a white dwarf. This Neptune-sized world defies every prediction of cosmic demolition. When a star like our own sun dies, it does not go quietly. It swells into a monstrous red giant, a phase so violent it should incinerate any inner planets and violently disrupt the orbits of worlds farther out. This white dwarf, designated WD 1856+534, should have consumed and destroyed this very planet during its death throes. Yet there the world is, intact and orbiting perilously close. Its discovery was a complete accident, spotted by astronomers using a different method to study the white dwarf itself. They noticed a periodic, subtle dimming of the star's light, the classic signature of a transiting planet, and were stunned by the implication. This was a forbidden planet, a cosmic survivor that should have been annihilated. How did it possibly endure? The most compelling theory is a dramatic tale of gravitational pinball. The planet may not have always been in its current tight orbit. It could have originally been much farther out, a cold, distant world minding its own business. When the star began its transformation into a red giant, the gravitational chaos in the system could have flung the planet inward like a cosmic slingshot after a close encounter with a surviving Jupiter-like world. This new elliptical orbit would have brought it skimming perilously close to the dying star, but just far enough to avoid total destruction. As the red giant shed its outer layers and collapsed into the white dwarf, the planet's orbit was then circularized by tidal forces, leaving it in the seemingly impossible location we see today. This single, accidental discovery forces us to completely rewrite the final chapters of a solar system's life. It proves that planetary systems are not static, but dynamic and chaotic until the very end, with worlds being tossed around like marbles in a box. More chillingly, it offers a crystal ball into the fate of our own solar system. Billions of years from now, when our sun bloats into a red giant, Mercury, Venus, and likely Earth will be consumed. But this forbidden planet shows us that worlds like Neptune, and perhaps even Jupiter and Saturn, might not only survive the inferno, but could end up in new, unexpected orbits around the white dwarf that was once our sun. The cosmos is far more resilient and far stranger than we ever believed. Deep within the churning chaos surrounding a black hole, a rhythm was found. While sifting through old data from a stellar mass black hole system, astronomers spotted something astonishing in its X-ray emissions, a steady, repeating pulse. This was not random noise, it was a signal with a clear tempo, a cosmic heartbeat echoing from the very edge of oblivion. They named this phenomenon a quasi-periodic oscillation, a rhythmic flicker in the intense X-ray light generated by superheated matter spiraling into the black hole. Think of it like a lighthouse beacon, but one shining from the most violent place imaginable. The existence of this rhythm is a profound clue, a direct window into the extreme physics playing out just outside the event horizon, the point of no return. The heartbeat is born from the black hole's accretion disk, a vast, flattened whirlpool of gas and dust being torn apart by unimaginable gravity. As this material spirals inward, it heats up to millions of degrees, emitting the X-rays we can detect. But the flow is not perfectly smooth. The leading theory suggests that the inner edge of this disk is unstable, flaring and flickering in a regular pattern. One compelling idea is that the entire inner disk is pulsating, expanding and contracting like a beating heart. With each beat, more hot material is dumped toward the event horizon, causing a corresponding spike in X-ray emissions. Another possibility involves blobs of material orbiting in a tight, rhythmic dance at the very inner edge of the disk, their motion creating a regular flash as they pass a certain point. This steady pulse allows scientists to probe regions of space-time warped by gravity to an extreme not possible anywhere else. By studying the timing and stability of this heartbeat, they can effectively weigh the black hole and measure how fast it is spinning, two of its most fundamental properties. The mere fact that we can detect such a precise rhythm from the brink of a black hole is a testament to the underlying order within the cosmos' most chaotic environments. It is a signal that even in the face of absolute darkness, there is a pulse, a pattern, a fundamental music to the machinery of destruction. The beating heart of a black hole reveals a cosmos of intricate patterns, but other structures hide their true nature in plain sight. Drifting through the Coma cluster, a vast collection of galaxies over 300 million light-years away, lies a ghost. It was spotted in a relatively small telescope array, the Dragonfly Telephoto Array, which was specifically designed to look for the faint, extended glow that other telescopes miss. Astronomers were hunting for large, diffuse galaxies when they found Dragonfly 44. At first glance, it appeared unremarkable, a dim, fuzzy patch of light with so few stars it was classified as an ultra-diffuse galaxy. It seemed insignificant, a wispy cosmic cloud, but its tranquility was a perfect illusion. When scientists studied its motions, they realized something was profoundly wrong. They measured the velocities of its globular clusters, the dense swarms of stars that orbit the galaxy's core. These clusters were moving at breathtaking speeds, far too fast for the galaxy's visible mass to hold onto them. According to the laws of gravity, such velocity should have torn the entire galaxy apart, sending its stars and clusters flying into the void. The only possible explanation was that Dragonfly 44 was anchored by an immense, invisible source of gravity. The calculations revealed a shocking truth. This faint, ethereal galaxy, which emits only 1% of the light of our Milky Way, has nearly the same mass. Over 99.9% of that mass is dark matter. We are not looking at a small collection of stars, but at a cosmic titan, a galaxy made almost entirely of stuff we cannot see. It is a dark mirror of our own Milky Way, a phantom doppelganger whose true form remains utterly hidden. How does a galaxy form with almost no stars, yet so much dark matter? Does it represent a failed galaxy, one that gathered its dark matter halo but never managed to convert much of its gas into stars? Or is it a remnant, a galaxy that had its stars stripped away by tidal forces in the crowded cluster, leaving behind its dark matter skeleton? Dragonfly 44 forces us to confront the unsettling possibility that the universe might be filled with these dark galaxies, vast, invisible empires that have been hiding in the faint shadows of the night sky all along. The cosmos is a place of phantoms and impossible giants, but perhaps no recent discovery has shaken our fundamental timeline as profoundly as the first images from the James Webb Space Telescope. This monumental observatory, designed to peer back to the dawn of time, has done exactly that, but it has shown us something we never expected to see. In the deepest, reddest images corresponding to a universe only a few 100 million years old, the telescope found not just infant galaxies, but cosmic titans. These galaxies appear massive, structured, and mature, filled with old stars, as if they had been forming for far longer than the age of the universe at that point should allow. According to our most trusted models of cosmic evolution, these galaxies should not exist. They are simply too big, too soon. This is not a small discrepancy. It is a direct challenge to our understanding of how the universe built its first structures, sparking what some scientists are openly calling a crisis in cosmology. How could such order and maturity arise from the primordial chaos so quickly after the Big Bang? The debate now rages between two equally profound possibilities. The first is that our standard model of cosmology, the very bedrock of modern astronomy, is flawed or incomplete. Perhaps dark matter behaved differently in the early universe, clumping together faster than we thought possible and seeding the rapid growth of these galactic giants. Maybe gravity itself operates in ways we do not yet understand on the largest scales. The second possibility is that we are misinterpreting what we are seeing. Could dust in these early galaxies be reddening their light, making them appear more distant and therefore younger than they truly are? Or are we witnessing the blazing light of voracious supermassive black holes, whose intense energy mimics the signature of a vast population of stars? Either answer leads to a revolution. If our models are wrong, we must rewrite the first chapters of cosmic history. If our interpretation is flawed, we must learn to see the infant universe with entirely new eyes. The James Webb Space Telescope, in its quest to confirm our story of creation, has instead handed us a beautiful, confounding mystery, proving that even our most foundational theories are subject to the unpredictable evidence of the cosmos. That single, brilliant flash from our galactic magnetar gave us a key, but the lock it opened revealed a door to a much deeper mystery. For years, every other fast radio burst had been a one-off event, a cosmic firecracker that flashed once and was never seen again. This pattern pointed to catastrophic, self-destructing sources, like two neutron stars colliding in a final, fatal embrace. But then, astronomers sifting through old data from the Arecibo telescope found something that shattered that simple story. It was a burst from a source catalogued as FRB 1211-2, and it burst again and again and again. This was the first repeating fast radio burst ever discovered, and its existence completely rewrote the rules. A collision is a single, violent event. It cannot happen twice in the same place. The fact that this source could fire off multiple bursts meant it had to be powered by an object that could survive its own immense outburst. The hunt was on to pinpoint its home. After a painstaking campaign using the world's most powerful radio telescopes, they succeeded in tracing the repeating bursts back to a surprising location, a tiny, faint dwarf galaxy over 3 billion light-years away. More specifically, the bursts were emanating from the extreme environment of a highly magnetized neutron star, similar to the magnetar in our own galaxy, but situated within a dense nebula of plasma. This solved one part of the puzzle, confirming that at least some of these bursts come from these incredibly dense magnetic stellar corpses. Yet, the exact mechanism that causes these stars to unleash such titanic, repeating radio shrieks remains one of the great open questions in astrophysics. The leading theory suggests that the star's unimaginably powerful magnetic field, trillions of times stronger than Earth's, can get tangled and stressed. When these field lines suddenly snap and reconnect, they release an explosive torrent of energy that we see as a burst. But why do some magnetars burst only once while others, like FRB 1211-2, become prolific repeaters? The answer may lie in the chaotic environment surrounding it, perhaps fed by a companion star or swimming in the debris of its own violent past. This one repeating signal, found by chance in archived data, transformed fast radio bursts from cosmic curiosities into a vibrant new field of astronomy, proving that the universe's most powerful explosions are not always an ending, but can be a persistent, if unpredictable, cry in the dark. A streak of light against the cosmic dark was the first clue. Astronomers using the Hubble Space Telescope were studying a distant galaxy when they noticed something impossible. A brilliant, linear trail of young blue stars stretching over 200,000 light-years, double the width of our entire Milky Way. At the tip of this stellar highway was the source of the chaos, a supermassive black hole hurtling through intergalactic space at millions of miles per hour. It had been forcibly ejected from its home galaxy, and in its wake it was sowing a garden of new suns. This was a runaway titan, a cosmic fugitive on the lam. How does a black hole weighing as much as 20 million suns get kicked out of its own galaxy? The answer lies in the most violent divorce in the universe, the merger of two supermassive black holes. For years, this has been a cornerstone of theoretical astrophysics. When two galaxies collide, their central black holes eventually sink to the core of the new combined galaxy, entering a gravitational dance. As they spiral closer, they radiate energy in the form of gravitational waves, ripples in the fabric of spacetime itself. If the merger is lopsided, if the two black holes are of unequal mass or have misaligned spins, the final blast of gravitational waves can be shot out in one preferred direction. Think of it like the recoil from a rifle. The black hole that forms from the collision gets a monumental kick, a gravitational wave rocket boost so powerful it can blast the newborn monster clear out of its galactic core. This runaway black hole is the first tangible evidence of that incredible recoil. But the trail of stars is the real masterpiece of this cosmic accident. The black hole is not traveling through a perfect vacuum. It is plowing through the sparse gas that lingers between galaxies. As the black hole rams into this gas at tremendous speed, it compresses and shocks the material. This compression triggers a frenzy of star formation directly behind the speeding Titan, like a cosmic plow turning interstellar soil into a furrow of brilliant new suns. The black hole itself is invisible, a dark engine of gravity, but the luminous trail it leaves behind is a perfect roadmap of its escape. If this interpretation holds, it is a direct observation of one of the most dramatic processes predicted by Einstein's theory. It shows us that galaxy evolution is not always a gentle merging, but can be a violent, chaotic event that can see the very hearts of galaxies torn out and sent careening into the void. It raises a tantalizing question: how many of these lone, star-forming phantoms are drifting through the blackness between the galaxies, their central engines silent and unseen? That runaway black hole showed us the universe's violent side, but a quieter, more profound discovery was happening at the very edge of observable reality. The cosmos was not just expanding, it was accelerating. This revelation came not from a single eureka moment, but from the careful, patient work of two rival teams in the late 1990s. Both were using distant supernova as cosmic mile markers, aiming to measure how much the universe's expansion had slowed down since the Big Bang. They were searching for the deceleration parameter, a value that would tell us the ultimate fate of everything. Would the universe eventually collapse in a big crunch or coast forever toward a cold, dark end? The answer they found was neither. The data from these exploding stars, located billions of light years away, was unmistakable. They were fainter than they should have been. Their light had traveled across unimaginable distances, and instead of showing a universe breaking under its own gravity, it revealed one that was speeding up. It was as if you threw a ball into the air, expecting it to slow and fall back, only to watch it shoot away from you faster and faster into the sky. The shock that rippled through the world of physics was absolute. This was not a small correction, it was a complete overturning of a fundamental assumption. Something was fighting against gravity, a mysterious, repulsive force permeating the vacuum of space itself. Scientists gave this unknown force a name: dark energy. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, had made the same staggering discovery completely independently, a convergence that left no doubt about the result. They had stumbled upon the dominant ingredient of our universe, a component that makes up about 68% of all the mass and energy in the cosmos. Yet we have no idea what it is. Is it a property of space itself, a constant energy density as Einstein once proposed and then discarded as his greatest blunder? Or is it a dynamic field, a fifth fundamental force that has only now begun to dominate the cosmos? The discovery of dark energy humbled science. It showed that our most cherished theories were incomplete, that the universe is ruled by a phantom force we cannot see, touch, or directly measure. It is the ultimate cosmic anomaly, a ghost in the machinery of reality whose faint, repulsive breath is sculpting the destiny of every galaxy, star, and planet, pushing them apart on a journey into an ever more isolated and dark future. The phantom force of dark energy shapes the cosmos on its grandest scale, but back within our own solar system, a different kind of ghost is suspected to be pulling strings. Far beyond the orbit of Neptune, in the frigid, dark expanse of the Kuiper Belt, a handful of icy worlds are not behaving as they should. Their orbits are peculiar, strangely clustered, as if an unseen shepherd is herding them. This is the indirect and accidental evidence for a potential ninth planet, a world whose existence is inferred not by a direct glimpse, but by the silent testimony of the tiny objects it commands. The story begins not with a new observation, but with a new way of looking at old ones. Astronomers Chad Trujillo and Scott Shepard, while studying the orbits of distant Kuiper Belt objects in 2014, noticed something odd. A small group of these objects, including the Sednoid Sedna with its bizarre, elongated path, shared an unexpected similarity. Their orbits were not randomly oriented. Instead, their closest approaches to the Sun were all grouped together in space, and their orbits were tilted in a similar way. The odds of this happening by pure chance in a placid solar system were astronomically low. It was as if you scattered a handful of marbles on a flat floor, only to watch them all roll toward the same corner of the room. This anomaly was a spark. When Caltech astronomers Konstantin Batygin and Mike Brown took up the puzzle, they ran exhaustive computer simulations of the outer solar system. The results were stunning. The only way to naturally produce the observed orbital clustering was through the gravitational influence of a massive, unseen planet. Their models suggested a world with a mass roughly 5 to 10 times that of Earth, tracing a vastly elongated orbit that takes it hundreds of times farther from the Sun than we are. At its most distant, this hypothetical planet 9 would be a faint, frozen speck, taking perhaps 10 to 20,000 years to complete a single journey around our star. The hunt for this hidden giant is now one of astronomy's great detective stories. Telescopes around the world and in space are scanning the predicted swath of sky where the planet's gravitational tugs suggest it might be. The search is painstakingly slow, like looking for a single, dimming ember in a continent-sized forest at midnight. Every other object in the solar system, from asteroids to distant galaxies, must be identified and ruled out. Each potential candidate is a flicker of hope that must be tracked for nights or weeks to confirm its motion. So far, the planet itself remains elusive. This lack of a direct sighting fuels a vigorous debate within the scientific community. Skeptics propose that the strange orbital clustering could be a statistical fluke, an illusion created by observational biases. Perhaps our telescopes have only looked in certain directions, and a more complete survey of the Kuiper belt will show the orbits are, in fact, random. Others suggest the collective gravity of many smaller, unseen Kuiper belt objects could be responsible, eliminating the need for a single large planet. Yet, the evidence for a planetary shepherd is compelling. The gravitational model not only explains the orbital clustering, but also predicts the existence of objects with orbits perpendicular to the plane of the solar system. In a remarkable validation, astronomers have since discovered several such objects, their bizarre paths aligning perfectly with the Planet 9 hypothesis. This hidden world, if it is real, would be a relic from the solar system's violent infancy, a core of a giant planet that was ejected to the frozen outskirts during a gravitational tug of war with Jupiter or Saturn. Its discovery would rewrite the final chapter of our solar system's family tree, revealing a long-lost sibling hiding in the perpetual twilight at the edge of our own cosmic backyard. These accidental discoveries share a common thread, a ripple effect that transforms our entire understanding of the cosmos. Each one began not with a grand plan, but with a scientist willing to embrace a glitch in the data, an anomaly that refused to go away. The story of the cosmic microwave background is a perfect testament to this. Arno Penzias and Robert Wilson could have easily dismissed that persistent hiss as a faulty instrument, an irritation to be tuned out. Instead, their dogged pursuit of the mundane, even to the point of cleaning pigeon droppings from their antenna, led them to the echo of the Big Bang itself. That single act of investigating a nuisance did not just solve a technical problem. It unlocked an entirely new field of cosmology, giving us our first reliable baby picture of the universe and forcing a complete rewrite of every astronomy textbook. Decades later, the mystery of fast radio bursts followed a similar path. When that first brilliant millisecond flash was found in archived data, it was so bizarre that many wondered if it was merely terrestrial interference. But astronomers did not simply shrug and move on. They kept looking, developing new techniques and dedicated telescopes to chase these cosmic will-o'-the-wisps. This pursuit, born from the curiosity about a single, accidental signal, has since blossomed into a vibrant new branch of astronomy, revealing a previously hidden population of extreme magnetic stars and cataclysmic events. The true breakthrough in science often arrives not when we find the answer we were looking for, but when we have the humility to admit we have found a question we never thought to ask. It is the open-mindedness to consider that a drifting spacecraft, an annoying hum, or a star that flickers strangely is not an error to be corrected, but a door to be opened. Each of these chance encounters forced us to look at the universe from a new angle, proving that the greatest tool in discovery is not always the telescope, but the prepared and curious mind behind it. The most profound cosmic mysteries often slip past automated algorithms and professional scrutiny, detected instead by the keen eyes of amateur astronomers and the relentless gaze of telescopes built for entirely different quests. Consider the Kepler Space Telescope, a mission designed with a single, focused purpose to find planets orbiting other stars by watching for the minute dimming of their light. Its true legacy, however, may be the chaos it revealed. Kepler's unblinking stare at a single patch of sky generated a flood of data so immense that scientists could not possibly analyze every twinkling star themselves. This data deluge created an unexpected opportunity, an open invitation for the world to join the search. Platforms like Planet Hunters and Galaxy Zoo emerged, turning cosmic discovery into a collaborative global endeavor. Here, volunteers from all walks of life, teachers, artists, retirees, and students, began sifting through the light curves of distant suns. It was these citizen scientists who first noticed the bizarre, erratic dimming of Tabby's star, a pattern so strange it defied all conventional explanation and sparked a worldwide scientific debate. Without their collective curiosity, that cosmic enigma might have remained buried in the noise, just another unremarkable data point. Similarly, the Pan-STARRS telescope in Hawaii was engineered to scan the heavens for near-Earth asteroids, potential threats to our planet. Its systematic patrol of the sky, however, caught the fleeting visit of Oumuamua, our first known interstellar guest, an object whose peculiar acceleration and shape continue to puzzle astronomers to this day. This was not its intended target, but a chance discovery that opened an entirely new chapter in planetary science. Orbiting above the distorting effects of our atmosphere, the Hubble and James Webb Space Telescopes have become legendary not just for their planned observations, but for their serendipitous revelations. Hubble's iconic deep field image, for instance, was a risky gamble, pointing the telescope at what was thought to be an empty patch of sky. That single image, filled with thousands of previously unseen galaxies, forever changed our perception of the universe's scale and richness. It was an accident that redefined our cosmic perspective. These instruments, both on the ground and in space, function as giant digital nets trawling the ocean of the cosmos. They are not always hunting for specific prey, but by casting a wide and sensitive net, they inevitably catch the strange and the wonderful, the anomalies that challenge our understanding. The next great discovery might not come from a lone astronomer in a domed observatory, but from a nurse in Norway or a mechanic in Michigan, staring at a computer screen after putting the children to bed, who notices a star flickering in a way that no one has ever seen before. This partnership between human intuition and mechanical precision is the new engine of discovery, proving that the universe's greatest secrets are often hidden not in the darkness, but in the plain sight of shared data. Jerry Amon's hand trembled as he circled that string of characters on the computer printout, his scribbled "wow" echoing in the silent room. He was not witnessing a planned result, but a profound anomaly that would define his career and haunt astronomy for decades. This human moment of stunned recognition lies at the heart of every accidental discovery. For every universe-altering breakthrough, there is a person, often initially baffled, staring at a piece of data that simply does not make sense. Science, in the popular imagination, is a methodical march toward truth. The reality is far messier, a story of stubborn intuition, frustrating dead ends, and the occasional glorious accident that arrives like a lightning strike. Arno Penzias and Robert Wilson spent months convinced their work was being ruined by pigeon droppings, only to learn they were hearing the faint whisper of the Big Bang itself. Their triumph was born not from a eureka, a moment of instant understanding, but from the tedious, frustrating process of eliminating every possible mundane explanation until only the extraordinary remained. They faced initial skepticism, with some in the scientific community questioning their methods, unable to believe such a monumental signal could have been found so casually. The story of the pioneer anomaly is a masterclass in scientific dedication. For years, a small group of physicists were obsessed with a deviation so tiny most would have dismissed it as instrument error. They became detectives, tracking down decades-old engineering documents and blueprints, speaking with retired technicians to understand every bolt and wire on the vintage spacecraft. Their eventual solution, that it was the gentle push of heat from the spacecraft's own systems, was not a dramatic revelation but a hard-won victory of meticulousness over mystery. They proved that the universe whispers its secrets, and you must lean in very close to hear them. Then there is the tale of Vera Rubin, who was initially discouraged from pursuing astronomy, yet her meticulous measurements of galaxy rotation curves revealed a discrepancy so fundamental it could not be ignored. The stars at the edges of galaxies were moving far too fast, threatening to fling them apart. The data was clear, yet the implication that most of the universe's mass was invisible was so radical it faced immense resistance. She was not looking for dark matter, she was simply following the data wherever it led, even when it led to a conclusion that overturned our understanding of cosmic structure. Her perseverance in the face of skepticism paved the way for one of cosmology's greatest mysteries. These stories reveal a universal truth about discovery. It is not a cold, mechanical process. It is fueled by human curiosity, stubbornness, and sometimes sheer luck. It requires the courage to announce a finding that seems impossible, to withstand the raised eyebrows of colleagues, and to embrace the beautiful, chaotic truth that we do not have all the answers. The next time you look up at the stars, remember that our map of the cosmos was not drawn by an infallible hand, but by people who are often just as surprised by what they found as we are. From a single, circled word on a printout to the faint heat of a forgotten spacecraft, our journey through these 25 anomalies reveals a cosmos built not just on laws, but on glorious, unpredictable accidents. We have seen stars that flicker under colossal dust clouds, galaxies made almost entirely of invisible matter, and interstellar visitors whose origins are still debated in labs and living rooms. Each one began as a blip in the data, a nagging inconsistency that a curious mind refused to ignore. The universe, it turns out, is not a tidy library where every book is perfectly catalogued. It is a vast, chaotic workshop filled with half-finished projects, strange tools, and blueprints we are only just learning to read. The greatest discoveries were not the ones we went looking for, but the ones that found us, whispering from the static or tumbling unexpectedly into view. This is the true heart of exploration, the understanding that for all our planning and powerful telescopes, the cosmos still holds the capacity to astonish us. The next great revelation might not come from a billion-dollar observatory, but from you looking at public data on a home computer, or from a student noticing a pattern everyone else overlooked. It is a reminder that wonder is not a resource we have depleted, but a constant, humming background radiation of possibility. So the next time you find yourself under a clear night sky, take a moment to simply look up. Remember that every one of those points of light and the immense darkness between them holds secrets waiting for a moment of chance, a question asked, and a mind open enough to be surprised. The greatest anomalies are still out there, hiding in plain sight.